Okay, let's take a look at friction drag determination and drag buildup, particularly at other elements on the fuselage that require some estimates of both friction drag and pressure drag. And namely, that's going to be things such as the fuselage and pylons. So first, to remind ourselves, what we're looking at is the entire drag polar. Now, the induced drag portion of this curve, right, that's the easy part. What we really want to focus on is this friction drag element, which remember is made up of both the friction drag, so this is the primary piece down here, and whatever associated pressure drag you have along with that. And we break this out into lots of different ways. You know, we call it the form drag, the profile drag, which includes both the form drag and the friction drag, and all these other little elements that come in called the friction, or sorry, the interference drag. So it's this induced part that's the easy one. So this half of the equation right here. So all we have to worry about is the overall geometry. But it's breaking out these other elements, you know, which part is the friction, which part is the pressure, and it's not always a very easy thing to do. In fact, it's usually pretty complicated. So what we're going to really focus on is just the two elements where we try to look at both the friction drag and the pressure drag and just keep it as simple as possible. And what we have to worry about is we keep in mind that this thing is a function of the attitude of the aircraft, the Reynolds number, the Mach number. So as we're changing our operating points of the aircraft, we're also going to be changing the values of both the CDF and CDP. So even though for our design concept, we're going to be focusing just on one overall prediction of these values, they will fluctuate quite a bit, both based upon the aircraft operating conditions, speed, altitude, as well as the aircraft operating configurations, such as gear stowed, geared up, flap stowed, flaps down. So if you recall, what we're trying to do is really develop a component drag buildup process. And as we talked about in class, we will try to use a library of different drag coefficients for various shapes, which each one of them has a certain reference area, and then we normalize that by our reference area for the aircraft, which is the wing area. And then that gives us a normalized value. Then what we can do, of course, is just build those up into CD components for every different component on the aircraft. And this is the example we looked at, Piper Cherokee. Start off with the major elements, wing, fuselage, the empennage, and then we start adding all the different pieces on, calculating that CD value for each one of those. And you'll want to be building a spreadsheet up for this for your any particular aircraft that you're analyzing. And this will allow you then to develop an overall estimate for CD naught. Now, the two components of this that we want to focus on is the skin friction, and then we'll talk about the pressure drag. The skin friction out of the two is kind of the easier one, because if we know what the surface area is, then we can get a really good estimate of that skin friction. The trick becomes determining which part of this is laminar and which part of this is turbulent. Again, we go back and use our flat plate models that we developed in undergraduate fluid mechanics, so that way we have a skin friction estimate for laminar flow and a skin friction estimate for turbulent flow. And notice they are very different values. That turbulent equation is going to give you a much larger value for CF than laminar. So predicting which one is going to be which is very important. Now what we have to do then is, if we know what this is, right, and let's just assume we already know what the breakdown between laminar and turbulent is going to be, then it's a matter of determining how much overall area that you have on the aircraft. And what we use for this is the what's called the wetted area. And so that wetted area is the overall total surface area of the aircraft. Now, if we go back and look at these skin friction values, again, let's just assume that, you know, for the most part on our aircraft, not on our wing, but on our aircraft, our skin friction is going to be turbulent, our flow is going to be turbulent, and we'll be using the turbulent skin friction equation accordingly. Then, we can estimate the entire value of the skin friction coefficient for the aircraft. What you'll notice, this tends to be a little bit higher than just using the basic prediction from this equation, and that's due to all the other things and components that you have on the overall aircraft. So those little pieces and things that you have to account for. So it's the total area of the aircraft. So how we account for that is getting what's called the wetted area. And the best way to think of this is if you take the aircraft and you dunk it in water, any part that gets wet is calculated or added up to the total wetted area. So if we use that estimate then for the skin friction coefficient, we take that wetted area and then we normalize it by the wing area of the aircraft, that gives us an estimate for our total friction drag coefficient for the aircraft. What you'll notice is a couple of examples. Something like a B2, a flying wing, that's going to have your lowest ratio of wetted area to wing area because all you're essentially doing is more or less doubling the wing area. Now you have the top surface, which is the planform, and then the bottom surface, plus whatever else that you've added on top of that. So if you had a flat plate wing, that would be your minimum possible wetted area, which would be a value of just over 2. Because you still have to account for the thickness and other things. And then you add things like a tail surface or engine inlets or whatever, then that's going to increase above that too. And so everything on top of that then is going to have a value much greater than 2. Typical transport aircraft are going to be in the range of 6 to 7 or so. Now, we have a tool that we've developed in that allows us to estimate this. So as typical, we have to put in our aircraft operating conditions and our planform area, and then based upon wetted area estimates and estimates of the aspect ratio, so thickness to chord, or length to diameter. So the chord, this is length to diameter and not lift to drag ratio. We can calculate the Reynolds number, and then from that determine how much that section is going to be laminar or turbulent. Now, for the wing, this is kind of the hardest part, right? Because your flow will tend to be laminar near the leading edge, and at some point it's going to transition to turbulence. This is where you have to either go back to measurements or predictions such as X-foil to determine where that transition point is going to be. How much of your wing is laminar, how much of your wing is turbulent. For most everything else in the aircraft, as long as it's not a lifting surface, such as a horizontal or vertical stabilizer, you can assume that it's going to be completely turbulent. The flow is going to transition very, very quickly to turbulence due to the basic nature of the flow or the geometry, such as surface roughness of the overall aircraft structure itself. So once you put in that estimate then for laminar flow, then it's going to calculate what the skin friction is, and then using that wetted area value, tell you what an estimate is for that CD naught component, and then add up to a value of CD naught. We've given 2 examples here, one for the MLB unmanned aircraft, and then another for the F-102. So let's go to that real quick and just look at this as an example. And so what you'll notice here for this particular example again, your values of cruise altitude and Mach number are going to play a role in determining what your flow velocity is going to be, as well as density and viscosity, which is going to determine your Reynolds number. That's the thing that really plays a role in determining what the value of the skin friction coefficient is going to be, whether it's laminar or turbulent. Both of those equations from the flat plate models are based upon the Reynolds number. So you put in estimates for your wetted area, for the fuselage, for the wing, the tail. We've added other components on here, nacelles, gear, and miscellaneous. And then you have a reference length, which again is important for determining that Reynolds number, and then an aspect ratio. So thickness to chord or length to diameter, depending upon the particular geometry that you have. And then this, you do have to make that estimate. And this way you can play around with it and notice what that value is going to be. So for example, if you make your wing completely turbulent, right? How does that change your overall drag? So we go from a drag coefficient of 0.025 or 0.008 for that component, where if we go completely laminar, right, we drop that drag down significantly for that particular value. Again, you can see the power in trying to make your wing completely laminar in this particular case. Okay, so again, this gives you at least a trade study tool or sensitivity analysis tool that you can start playing around with these various components. Worst case scenario, make everything turbulent, right? Completely turbulent flow, and that's going to tell you what your maximum value is going to be for a turbulent scenario. Just assume that your aircraft is now completely dirty. All right, let's go back then and look at the rest of the aircraft in terms of overall pressure drag. And this is primarily going to affect things like the fuselage, engine nacelles, and pylons. Any type of asymmetric structure, fuselage is going to be the most egregious example of that. So let's look at a typical transport configuration. So what we're going to be focusing on here is the fuselage. So we can break this up into three separate elements: the nose cone, the cabin, the center section, right? So we can assume that that's going to be, some kind of a cylinder type of shape, and then the tail cone. Now let's look at the nose cone first, right? Because again, we could just think about this with basic flow transpiring over the entire fuselage, and we're going to ignore the other elements for the time being. So if we break this down, what we need to do is calculate the pressure drag and the skin friction drag, right, or shear drag from each one of these elements across the entire length of the fuselage. So now we can break it up from the total drag is going to be pressure drag and friction drag for the nose cone, pressure drag and friction drag for the center section, pressure drag and friction drag for the tail cone. And we have to estimate the values for each one of those. So let's look at the nose cone first. Now this is very similar to what you have on the leading edge of a wing. You have a stagnation point, so you end up having an area of a greater pressure due to your reduced velocity. And as the flow starts to accelerate over the curved section, then you end up having a pressure drop. And as a good first guess, the overpressure that you have from the stagnation area region is balanced out by the underpressure drag that you have, or underpressure value of that drag that you have on the rest of that nose cone. So, or the area under this part of the curve is balanced out by the area under this part of the curve. So you can typically take that to about be zero. And from a design standpoint, that's really kind of what you want to design for, or right, try to make this section larger than this section. But at the very least, if you can balance this out, then that means you don't have to worry about the pressure drag from your nose cone. So now if you go back and look at this, so the pressure drag value for that particular component, you can estimate to be zero. Likewise, if you look at the cylinder section, you have no separated area in here, assuming this is aligned with the free stream, so the pressure drag on the center section is also going to be equal to zero. Then all you're left with is the pressure drag from the tail cone, right? We're going to call that the base drag. So now we have four drag components that we have to estimate. The friction drag, which we've already talked about, and now the pressure drag for the tail cone. So how do we go about that, and how do we optimize then this overall design of this? So we break it out. The total fuselage drag is going to be equal to that friction drag piece plus the overall base drag piece. And we can put this into two components: the friction drag, which we've already discussed, as well as that overall base drag, to try to calculate the overall CD value for the entire fuselage itself. Now we use a relationship from Horner's drag book where he suggests that the base drag is going to be equal to 0.029 divided by the square root of the friction drag times that wetted area to the base area ratio. And so then if you take that relationship and plug that back into the rest of your equation, then that's going to give you an estimate for your overall drag coefficient for the fuselage. Again, this previous part we've already talked about, right? That's nothing more than that wetted area relationship plus that friction drag piece right here. And again, when we normalize that and put that back in, this is the equation that we end up with. Now what we can do then is start to break this out, and if you look at the wetted area value, right, for that entire fuselage, we can put that into the components of the length of the fuselage, cross-sectional area, the aspect ratio of the wingspan, and come up with an equation for that. And we're going to break those up into what we call this fuselage ratio, or the fineness ratio of that fuselage, and then we'll just call this a K factor, so we don't have to keep writing that all the time. And we can do the same thing for the tail cone section, or that base drag. And so these are simple geometrical relationships. Then we can put that back into the previous equation and write that in terms of these geometry components of K and F, which again are just ratios of our overall area. Now what you end up with then is a fuselage drag equation that says, well, your friction drag is going to increase as F gets larger, so you have a friction drag component here, and then your base pressure drag is going to be decreased as F gets larger, so it goes as 1 over the square root of F. And so that means that as you increase one gets bigger, decrease one, or increase one drag component gets bigger, the other drag component gets smaller. So when you add these two up, obviously you end up with a minimum somewhere in the middle. And basically, you can think about this in terms of overall area, and then this is in terms of your fineness, right? As you take that drag, or that the tail cone out to a very, very pointy end, you end up reducing your pressure drag, but at the same time increasing your surface area, so increasing the overall friction drag that you have. So then you can optimize this and say, oh, okay, I'm going to take this equation, then optimize the design of my fuselage to come up with the minimum drag value. Now what you find if you do this for low Mach numbers is you end up having an optimum somewhere around F value of 3, which means you have a pretty fat fuselage. So that gives you a length to diameter ratio, right? That's fairly low. So your diameter that you have is 1/3 of your length. So you end up having a really fat fuselage. So this is not very practical for most transport aircraft designs. But you can use it if you're trying to, transport large things such as other aircraft fuselages, and so they actually see that in some designs. And so you end up for most transport aircraft essentially sacrificing friction drag to get rid of some of that pressure drag. So you have a low pressure drag value and a much higher friction drag because of that. But you do see this ratio find its way into other designs such as blimps or dirigibles, where you end up having a pretty low value of that fineness ratio. Now where you do see this happen at higher Mach numbers, very high value of this is for high-speed aircraft design, such as supersonic aircraft like the Concorde, where you end up having very, very tiny cross-sectional areas. And that's where your wave drag starts to come into play. So if you could do a comparison between typical subsonic transport aircraft and supersonic transport aircraft, the starkest difference is in that length to diameter ratio of the fuselage. You'll note if you look at something like the 737, you do have a lot of asymmetry between the nose cone section and the tail cone section. Trying to reduce that drag from the nose cone, gives you similar type of designs between the nose cone and the tail cone. But keep in mind what you're trying to also do here is minimize your manufacturing costs as well as logistical considerations for the overall aircraft, how you're storing passengers on board and everything else. So let's go pull the example up for the fuselage drag component, and this is going to be most beneficial when you're trying to predict components of that wave drag as well and optimize the ratio of your length to diameter ratio of your fuselage. So if you go back and look at this particular spreadsheet, again, standard input parameters, but now you have dimensional data for your fuselage. Diameter, length is a function of that diameter, so your F value here, and unfortunately we have defined a different form factor, which you'll see in the literature. Don't worry about these terms necessarily. These are used in the equations down below, and then your reference area for your fuselage, which again is going to be your wing area. And this, what it does then is essentially fits a curve to that shape and then calculates an overall value for that. So what I recommend that you do is actually use this in conjunction with the friction drag value to make an overall estimate and add this on as a component to that. And that gives you really good coverage for making an estimate of that overall drag value in terms of the friction drag plus the pressure drag. So using both of these components. And notice we break this out into your total CD naught, which component of that is due to wave drag, and which component of that is due to viscous effects or friction drag for your actual fuselage. So now what we talked about before then are relative values of total CD naughts for various aircraft examples. Transport aircraft are the most obvious one where we've seen a general improvement in this, primarily based upon values of that friction drag, trying to clean up the entire aircraft and make it more aerodynamic and reduce that friction drag burden as much as possible. But a portion of this is also due to reduction in overall pressure drag. And these give you pretty good benchmarks that you can start to work with. If you come up with a CD naught value that's going to be 0.005, you're probably going to be much too low. So you're not making a good estimate of that overall CD naught. And then likewise, if you end up with something that is even near 0.1, then your CD naught is going to be too high. So you really want to kind of look for a 0.015 to 0.02 range for a reasonable estimate of what that CD naught is going to be. Now keep in mind that, again, this is the most difficult thing to predict on that aircraft, what that actual value is. So going back and looking at additional examples is very, very useful to do. So this is one for the older model of the Gates Learjet. This is a model 25 from McCormick's text. What you'll notice here is two-dimensional aspect ratio or two-dimensional drag polar for an aspect ratio of infinity, and then your 3D drag polar values. This is essentially for your wing, and then this is for your entire aircraft. And when you do the drag breakdown on this particular system, you have the wing, the fuselage, the tanks make up the largest component of this, and then add on the tail that covers about 80% of your entire aircraft with those components. And so the other smaller pieces, nacelles and pylons, you can roughly take this aircraft and break it down into 10 separate components. So you don't have to break everything out and look at all the individual pieces. So 10 components is enough to come up with a really good drag prediction. Now what you will notice is when you start to make these estimates, again you can use these and make the estimates based on the tools that we've already developed in here. The one that's really missing is this interference drag component, right? And where's that coming from? Well, that is the sum of the parts is not the same as the whole. We're missing pieces when we take the CD of the wing and add it to the CD of the fuselage. What does interference drag mean? Well, you end up having an additional drag component when you start adding all these additional components and pieces up. So you have to be aware of that. Using a value of something on the order of 10 to 20% above your predicted value of CD naught by taking all these other pieces in, is a good conservative way to do that. To say, well, we can't really predict what our interference value is going to be unless we add all these pieces up, or build the aircraft or build an aircraft model and test it in a wind tunnel. So to be on the conservative side, I always recommend that you add an interference value in there on the order of a 20% or so to really take care of these last two pieces here that we don't have. We haven't talked about the gap and roughness effects. That's due to the fact that when you're manufacturing the aircraft, you will have different pieces as you overlap your structure together and your skin, gap effects that add additional drag as well.